This is Chapter 5, Section 1. This is the study of systems of linear equations. We're going to study linear systems. We're going to use the elimination method, and we're going to discuss the special systems and solving linear systems with three unknowns or three unknown variables. Example 2 and 6 are the examples that are covered in your e-textbook that I have put on our notes to cover. The first thing we want to do is talk about what all of this system of equations is doing. When you solve a system of equations, you're either finding where two lines intersect at one point, you're finding the one point of intersection, or you're finding out that the lines are parallel and there is no point of intersection, or you're finding out that it's the same line. And most of the work that you're doing, the point is to learn how to find that intersection. So most of them do have a point of intersection. So if we look at this, in your textbook, they give us a couple of equations. They give us the equation 2x minus y equals 2 and x plus y equals negative 2. And if I were to graph these two equations, they would look something like this, and these actually intersect at 0, negative 2. And one of them looks this way, and the other one looks something like this if you were to graph them. So these are two independent equations. They're not at all the same equation. There's no relationship. They're just two independent equations. And they have a point of intersection, which means they are a consistent system. We have a solution. These 2 points intersect at 0, negative 2. So what you're going to find out is when we solve a system of equations, we're finding where the lines intersect. Then the other possibility that could occur is that you may have an equation like 3x plus 2y equals 3 and 3x plus 2y equals negative 4. Notice the x and y's are the same, but the constant is different, which is going to indicate that you have parallel lines. Two lines that are, they're two independent equations, they're two different graphs, two different lines, so the equations are independent. But there is no solution. There's no point of intersection. So this is an inconsistent system. So the system is inconsistent. The equations are independent. But because they're parallel, there's no solution. So we write the solution set as being no solution. So notice again, two independent equations. They do have a point of intersection, and the answer is a single ordered pair solution. Or you have two parallel lines. Notice how they are familiar looking, but they have two or common among them, the x and y, but the constant is different. They're parallel lines. They are two independent equations, but they're inconsistent in that there's no solution, there's no point of intersection. So the solution set is no solution. The last example is I could give two equations. And it ends up being the same line. Notice how everything in this and this, look at this, everything here is double everything in the other line. So double the x would be 2x, double this negative y would be negative 2y, double the negative 3 would be negative 6. So if you were to graph this line, you went and found points, and then you went and found points. The first line would graph something like this. And then you went and got points and graphed this, it'd be the same line. It'd be one line laying on top of the other. So in this particular situation, the graphs are the same line, and there's an infinite number of solutions because this point and this point are common, this point and this point, every single point is in common with the other one of the other line. So this system is considered consistent because we have an infinite number of solutions, but we do have solutions. But the equations are not independent. It's the same line. So these are dependent equations. So that covers a lot of your vocabulary. So let's look at actually being given two equations and finding their point of intersection by solving the system by elimination. So the elimination method will lead to us being able to find the point of intersection. What we want to do is you want to eliminate one variable. So you can solve for the other one. I'm going to write the other variable. So I want to be able to add these two equations. So I'm going to add that up here. Add equations, or you can say add the system, to eliminate one variable so you can solve for the other variable. Well, if I add them right now, 3 and 2 is 5, -4 and 3 is -1y. It doesn't get rid of either one of those variables. So to do that, what I want to do is determine what would be the least common multiple of either the 3 and the 2, so that I can get rid of the x, or what would be the least common multiple of the -4 and 3 so that I could get rid of the y. Now, if you remember, when you add a positive and a negative of a number, like +3, -3, you get 0. So what I want is the least common multiple of one of these so that when I add, they cancel out. Notice this one's already positive and this one's already negative. So I think I want to get rid of the y's. That way I've already got the signs taken care of. But what I would have to do is I would have to multiply this equation through by 3 and this equation through by 4. Because what is the least common multiple of 4 and 3? This 4 and this 3. What would be the least common multiple? And it would be 12. So I need to multiply this whole equation by 3 so that I get a -12 here. I need to multiply this whole equation through by 4 so that I get a +12 here. And let's see what our new set ends up being. So 3 times 3 is 9x. 3 times -4 is -12y. And 3 times 1 is 3. Now I want to take the second equation. 4 times 2x is 8x. 4 times 3y is +12y. And 4 times 12 is 48. There's my key right there. Do you see what happened? So that I can add them together. Remember, add the system to eliminate one variable so you can solve for the other. But I had to do a little bit of work first. I had to get two of the values to be positive and negative of the same amount. So +12 and -12. Adding this together, I have 17x equals 51. Now you're able to solve for this other variable, which is x. So divide both sides by 17. So x is 3. Remember, you're finding the point of intersection. Here's an actual picture of it from your textbook. But you have just found the first part, the x is 3. Remember, it's an ordered pair, x, y. So you just found the x part. Remember from years of doing algebra, if you know what x is, you can substitute it in and find y. So substitute, found variable, value, to solve for other variable. I'm going to take my 3. It doesn't matter which one of my equations I go back to. I'm just going to go back to that first one. 3x minus 4y equals 1. I'm going to substitute in 3 for the x. I get 9 minus 4y is 1. So I'm going to subtract 9 from both sides. I get negative 4y is negative 8. Divide by negative 4 on both sides. Y is 2. There's your answer. So solving a system of equations allows you to find the point of intersection. Notice when they graphed these two lines, that was the point of intersection, 3, 2. Let's do another one. This one comes from You Try It in example 2 in your ebook. It's the button right next to example 2. So step 1, you want to get rid of one of the variables. You're going to do that by finding the same amount, the positive and negative of the same amount of one of those variables, so that when you add the two equations, one of that or that variable is eliminated. So again, I could get rid of the x. 3 and 5 both go into 15, so I'd need a positive 15 and a negative 15. But I already see that one of these is negative and one's positive, so I want to get rid of the y, because I don't have to deal with trying to make one negative and one positive. I just have to get the right amount. So 5 and 6 go into 30. So I'm going to eliminate the y. The LCM of 5 and 6 is 30. So I'm going to multiply the top and bottom by the right amount so that I get 30, negative 30y and positive 30y. So the first equation I'm going to multiply through by 6. And the bottom equation or second equation I'm going to multiply through by 5. So that gives me a system. Multiplying everything by 6 in the top one, 3 times 6 is 18x. Negative 5 times 6, negative 30y equals, oh, I think I needed my little calculator. Let's see, 56 times 6. I bet you're faster at it than me. Getting it in there. I got 336. Alright, now we're going to do the bottom one. 5 times 5x is 25x. Negative, yes. 5 times 6 is 30y, I'm sorry. And 5 times negative 7 is negative 35. Works out great. My y's go out. So my 18 plus my 25 will give me 43x equals my 336. Add a negative 35 to it will give me 301. Divide both sides by 43. So x comes out to be 7. Now that I know x is 7, I've got the first part of my answer. And remember, if you know x, all you have to do is substitute into one of these equations. It can be the first one or the second one. I think I'm going to stay away from the 56. I'm going to substitute it into the second one. X is 7. 5 times 7 plus 6y equals negative 7. 35 plus 6y equals negative 7. So I'm going to subtract 35 from both sides. So 6y is equal to negative 42. Now divide both sides by 6. And I get y is negative 7. And there's your solution. Those two graphs intersect at the point 7, negative 7. Let's look at some special cases. So far we've done 2 where they actually had a point of intersection, but example 3 and 4, they don't intersect in one of these, they're parallel lines, and in the other example it's a system where it is the same line, so it has an infinite number of solutions. So this one is going to end up being no solution, no points of intersection, to infinite. Let's see what happens when we go to solve these two, why we know what our answer will be, as in no solution versus infinite number of solutions. In this system, when we go to solve, you might want to get rid of the x, or you might want to get rid of the y, because this is a positive and negative positive, just as easy to get rid of one as the other. So this time, let's get rid of the x's. So when I go to solve for this one, 3 and 6, the least common multiple is going to be 6. So I'm just going to make this equation 2 times bigger than it was. Let's come up with our system. So that would be 6x minus 4y equals 8. Negative 6x plus 4y equals 7. And look what happens. The x's are going to cancel out. The y's are going to cancel out and give me 0 equals 8 plus 7 is 15. When the x's and the y's cancel out, you've got a false statement. This is false. 0 does not equal 15. You know that the lines are parallel and there's no solution. There's no point of intersection. False means no intersection. Remember the graph and the picture we did? Remember how the x part and the y part were the same looking, but the values on the constants were different? Well, when we actually go to solve these, you find out that the x and y's canceled. When you tried to cancel one, you canceled both of them. So your 0 equals 15 is a false statement, and you know the lines are parallel. There's no point of intersection. Let's contrast that to example 4. Solving a system with infinite many solutions. In this one, we try to cancel out one of the variables. I'm going to try to cancel the x out. This is an 8, and 4 goes into 8. So I'm just going to multiply this through by 2. So I will have a system of 8x minus 2y is negative 4. And when I multiply the bottom equation by 2, I get negative 8x plus 2y equals positive 4. Notice when I go to add, cancel, cancel, cancel. I get 0 equals 0. That means it's the same line. So that means there's infinite number of solutions. So we give the answer, you can write it in words, infinite solutions. And the way to show it would be to say my answers lie from negative infinity to positive infinity. So how do I recognize an inconsistent linear system? I get the x and y's, the variables cancel. And I'm left with a false statement. How do I recognize a linear system with infinite many solutions? The variables cancel out. And I'm left with a true statement. Remember, an inconsistent system means there's no solution. that's why they worded it that way, but it means the lines are parallel. They don't intersect. We're going to stop the video on examples 1, 2, 3, 4, or 2, 3, 4, excuse me. And then we're going to do a new video that just covers a system with 3 equations. We've solved a system with 2 equations. So now let's look at 3 equations on the next video.